So the data points are 1, 2, 2, 1, and 4, 6, 5, 7, 6, 6, and 10, 12. Right? So we want to create three clusters out of this data point, or it appears that these are the three separate clusters. So let us see how our clustering algorithm works. So let's first try k-means clustering. And cluster, we have to select three cluster heads also. So the initial cluster heads are cluster heads 1, 2, 4, 6, and 6, 6. So let's see how does the algorithm work. How would we know the equation? Let's try it like this. How do we do it? We calculate distance of data points from each cluster head, and then assign the cluster. We are doing it for first time. Let's call it iteration. Iteration 1. So you calculate these values and tell me the number. Would this say that C1, 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 C2, and C1, C3? What does that mean, Ujjwal? So this C1 is distance of data point from C1. DC2 is distance of data point from C2, and DC3 is distance of data point from C3. So data point is shown above. So 1, 2 is the data point. 1, 2 is the data point. If you want to go with this data point notation, then we may call it as you are saying P1, P2, and so on. So distance of P1 from C1, as we can see, is 0, because both are same points, right? 1, 2, 1, 2. And we are using Euclidean distance here. What will be the distance of P2 from C1? It will be 1 minus 2 square, right? So the square root of 2, as they will say, 1.41. Distance of C1, C2, C3, right? So 2 minus 4 square plus 1 minus 6 square. Square root of 29. And so on. Third one is, and we know that the minimum, you can calculate it yourself, but we know that the minimum is C1. So C1 will be assigned to this. So data point 1 is assigned cluster 1 after iteration 1. Data point 2 is also assigned cluster 1 after first iteration, and so on. So finish this calculation and tell me the final assignment after iteration 1. I'm waiting for you to finish the calculation. Once you finish the calculation, put your answer in the message box and we'll move to the next iteration. So Urjit, now can you see the C1, C2, and C3 now? Okay. So P4 has 5, 7, and as we can see, distance from 5, 7 is square root 2 and square root 2 in both. Yes, so it is both. So it can be any one randomly, or you can have a convention that it goes to lower clusters. So go to the lower, assign to the lower index as a consistent rule. So C2 index is lower than C3. So while you are doing this computation, I am finishing my task. I think Shell has finished. P1, P2 got C1, P3 got C2, P4 got C2, and now P5 and P6 are in C3. So are you all getting the same answer? I think this is correct. Okay, Urjit also got the same answer. So is the calculation clear to everyone? Is there any question on the calculation? It's pretty simple, right? We are just calculating Euclidean distance. I don't want to spend much time on this. So now what is the next step? Calculate the new cluster head based on the cluster assignment that we do, which is mean of the points that you have assigned to that cluster. So C1 has 2 points, P1 and P2, right? As you can see. So that is 1, 2 and 2, 1. If you take mean of these two, it becomes 3 by 2, 3 by 2, right? So C1 is now 3 by 2, comma 3 by 2. C2 is the data point in C2 are 4, 6 and 5, 7. So mean will be 9 by 2, 13 by 2. And C3 is, what is C, weak point? 6, 6 and 10, 12. So 8, 8, comma 11 will be C3. So let us see how our cluster heads are moving. So initial cluster heads were 1, 2. This was initial cluster head. 4, 6 and 6, 6. So this green circle were initial cluster heads on which we run the first iteration of the algorithm. After first iteration, the new cluster heads are 1.5, 1.5. That is, cluster 1 has moved between these 2 points. So see, it is moving towards the mean of that circle. So it is trying to keep equal distance from both the points. Similarly, the second cluster head is 9 by 2, 13 by 2. So there is 4.5, 6.5 somewhere here again, right? And the third cluster head is, as we say, it is prone to outlier. It goes towards outlier. It is 8, 11. 8, 11 is correct. No, 8, 9. 8, 9. Yes, so these three dots are new cluster heads after iteration 1. Right? Are you with me so far? Any questions? Okay, share says it's clear. Okay, good. So now let's try one more iteration to see whether the cluster heads are moving or not. So let's repeat the procedure. Repeat the same computation, but now your cluster heads are different. And tell me the new assignment. I guess point 1 and 2 remain same. They are still closer to 3 by 2, 3 by 2 points. Right? So this both of these points, C2 and C3 have shifted towards left. So cluster 1 is, and the data in cluster 1 will remain. What will be your new cluster assignment after second iteration? P3 will be assigned to C1, C2 or C3. P3 will go to C2, right? And same for P4 also. If you see here, P4 is closer to again cluster head 2, so it should go to P2. Cluster assignment will change for P5. Now P5 will find itself closer to C2 than C3 because C3 has moved quite away towards outlier. Right? So new assignment for P5 will be C2 is towards C1. C1, P2 are in C1. P3, P4, P5 are in C2. P6 is C3. If you do the if you calculate equivalent distance for all of them, you should get this answer. Right? Are you getting this same answer? So I guess you are also getting the same answer. Tail has confirmed. So now cluster data has moved from cluster or clusters are changed. So we need to iterate one more time in this algorithm. So I remember that we keep on iterating as long as there are changes in the cluster assignment. So again, new cluster heads we need to calculate. So C1 remains same. C2 is now changed. It is average of 3 points. P3, P4, and P5. There is 15 by 3, that is 5, comma 9, 3. And C3 has only 1 point, which is before cluster head 10, comma 12. Right? Iterate one more time, but it will not change the assignment. If you want to try, you can try third iteration. But it will not second iteration. Sorry, third iteration, which is iteration number 2. You do go through ITR 3, but at the end of third iteration, you will again get C1, C1, C2, 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 and C3. And that cluster assignment has not changed and algorithm stop. Right? So this is how k-mean reaches to the optimal cluster. And at the end, you will have cluster. This, and this is what we have expected. Right? So these are the final clusters, which I shown through purple line, which we get through this algorithm. Now, if we talk about k-middle algorithm, can you tell me where the algorithm would differ from k-mean? Process will be same for k-middle. The only change is instead of calculating new cluster head as some point which is not part of data, the new cluster head are also from the data. So look at the data points inside the cluster. For example, in this case, cluster C1 has 2 points, P1 and P2. So look at the point P1 and P2 and choose any one of it as cluster head, the one which is minimum distance from all other data points. In this case, there are only two data points, so any one of them can be a good middle. If there are more than one data point, then you might want to look at you need to calculate all the distance between every pair of data points and choose the one which has minimum distance from all other points. Right? So that is the only different part in case of k-middle clustering. I see there is a considerable lag between the time when I speak and time you receive the audio or video. So I will wait for 1 or 2 minutes. Think about all the things that we have discussed and please ask me if you have any questions. Or please tell me if you have missed anything. So is everything clear? Any questions? The next type of clustering is called, okay, I said as a question, is there any case where new cluster changes every time in new iteration? Usually, yes, uh, because this is very simple data that we have taken as a classroom example, where we can directly see the cluster head and easily reach there. But in real world multi-dimensional data with so many points, data points, clustering doesn't emerge very obviously. And also, if you see the starting clusters that we choose, also has a role in deciding how many iterations you need to go through before you reach to the final cluster. In this case, we had chosen C1, C2, C3 in a way that it requires two iterations to reach to the answer, because one was in cluster 1 and 2 were in cluster 2. So only movement was from cluster 2 to cluster 3. Movement of centroid from cluster 2 to cluster 3, which you could finish in two iterations. What if the randomly selected initial cluster heads were all in the first, were all in the second cluster, let's say? So I mean, the cluster head that we had selected initially were 4, 6, 5, 7, and 6, 6. If you start with that, then you might need to do one or two more iterations before you reach to the cluster 1 and cluster 2 data points. Have I answered your question, Chaim? Okay. And another thing is, there are cases where data points keeps on jumping from one cluster to another. One obvious reason that you could see here is, in first iteration, you have seen that distance of point number, which one, P4, was same from C2 and C3 or something like that, isn't it? Or was from same from C1 or C2. And I said that choose the one which is lower index, and say C2, C1 is C2 is lower index, so let it go into C2. So this kind of decision we need to make. So sometimes it happens that a data point is at equal distance from both clusters. And if you choose to make random assignment, then iteration after iteration, it can jump from one cluster to another cluster. And your algorithm may not stop at all. So these are the cases which can put this algorithm in taking more iterations, which can make algorithms take more iterations. But that we can decide. That is easy to decide. So if you see that the changing is cluster heads are changing, but it is switching between the iteration. If you know that it is previous value and next value, it is just switching between previous and next value, then you can make algorithm stop. Any other questions? So if there are no other questions, let's move to the next clustering technique that we want to discuss. This is known as hierarchical clustering technique. So the previous one, we calculated distance, but it was more of a partitioning kind of technique. The k-means or k-midroid are called partitioning kind of technique, where you partition the data into groups. And the number of partitions or number of clusters are decided in advance before the algorithm starts. We also talked that this may not be very easy, or it may not be very easy to decide the number of clusters in advance. So in that case, what can we do? So this is an answer. Hierarchical clustering, which again works on distance calculation, again a distance-based technique, but it does not require number of clusters to be decided in advance. And for that, what it does is it works in two ways. One is bottom up, and second is top down. Since the top down version is possible, we had a top down version defined, but bottom up is usually a popular version. is used most of the time, and this is known as hierarchical. Agglomerative clustering. Let us see how does it work. So it takes starts with equal to number of data. Is complaining about voice. Yes. So I think there is a delay between the time when I speak and the time when it is used. Just I'm trying to speak very slowly, or I'm trying to also leave gap between uh, sentences. So hierarchical agglomerative clustering starts with number of clusters is equal to number of data points, and in every iteration, it merges the clusters with maximum similarity. So though it is called distance-based clustering, similarity is the measure used here. We know that similarity and distance are complementary measures, right? I think earlier we talked about this, but we can spend a bit some time here also. And it keeps on doing this. So repeat the process until you or all clusters are merged. Right? So we repeat the process until all clusters are merged into one. Let us see what we mean by this. Let us take the same data set and now let us say what we mean by this. Let me again bring this plot. Okay, let's not create a plot. Let's do it like this. So this is data point 1, 2. This is data point 2, 1. This is data point 4, 6, 5, 7, 6, 6, and 10, 12. So this is our data point. So now what we do is we calculate the distance or similarity between every pair of data points. And similarity means there are many similarity measures. The one which we like is called cosine similarity. Let's try cosine similarity. So cosine of C1 and C2. How do we calculate this? Cosine of P1, P2 is P1, P2 divided by value of P1, P2. That is equal to dot product 1 into 2 plus 2 into 1 divided by square root of 1 plus 4 into square root of 4 plus 1. Right? I hope you remember this. So that is 4 divided by 5. Isn't it? So similarity turns out to be 0.8. Cosine is a very powerful similarity measure. And most of the time, in many algorithms, you will see use of cosine rather than any other similarity. And I think you know the difference between cosine and Euclidean, but still, just in case if you have missed it, let me show you through graph what we mean by cosine and what we mean by Euclidean distance. So the 2 points we are talking about was 1, 2, and 2, 1. So this is 1, 2, and this is 2, 1. Now, when I calculate Euclidean distance, I calculate this. Right? Last time we talked about Euclidean distance and Manhattan distance. And when I talk about similarity, what do I talk about? I talk about this. I talk about this. Right? So are the vectors pointing in the same direction, or all the vectors pointing in the same direction are considered similar irrespective of their magnitude? So if you want to look at the magnitude, this difference in magnitude of the vectors pointing in the same direction, then you need to look at the Euclidean distance. If you are interested only in the direction, not the magnitude, then you want to look at the similarity. Right? So when we calculate the cosine similarity, pairwise dot product, it would be something like this, 0.8 between them. Is this clear? Are you with me on this? Any questions, or is this clear? Okay. So now what we do is here in of most similar points and merge them into clusters. So algorithm starts with example algorithm starts with 6 clusters. As I said, start with number of clusters is equal to number of data points. So we have 6 clusters at the beginning of the algorithm. 1, 2, 3, 4, 5 and 6. And then the algorithm will pick up the two most similar clusters and merge them. How do it? How does it do it? It calculates the similarity and merge them. So which two are most similar? I guess we have choice between 5766 and 1221. Right? Both have similar, but let's see on cosine similarity scale how are they different. We did for 1221. It was 5667. 5766. So the points are 5766. And the cosine similarity for them is 5 minus 7 into 6 minus 6 divided by all this. It turns out to be 6 minus 6 turns out to be 0. Sorry, did I make a mistake here? Oh, it will be 5 into 6 plus 7 into 6 divided by square root of 35 plus 49 into square root of 72. Something like this. So 5 into 6 is 30. 7 into 6 is 42. And so on. So calculate the similarity like this and merge the cluster. So let us say in first iteration we end up merging these two into one cluster with 2 points, 1, 2, and 2, 1. And then we could also merge this in the same iteration or in the next iteration with 5, 7, and 6, 6. And keep on repeating this process. So now we have 1, 2, 3, 4 clusters. And again, we calculate the similarity between them. So we calculate similarity between this and this. So now the question is, when you are calculating similarity between a cluster which has multiple data points, what will be your representative point? So again, one can be centroid or mean. It can be average, nearest, or farthest. So when you are calculating similarity between 1, 2, 2, 1 and 4, 6, 4, 6 has only 1 point, so that will be easy. But for 1, 2, and 2, 1, you need to convert it into a 1 point, with which you can calculate the cosine similarity of 4, 6. So either you take average of this 1, 2, 2, 1, which becomes 1.5, 2.5, or you can take the one which is nearest to 4, 6, or one which is farthest from 4, 6. Calculate the distance and calculate. So let us say we are doing average and then we merge. So then we will have a third cluster which is called 1, 2, 2, 1, and 4, 6, and so on. Similarly, you will merge these two clusters and it will make one cluster. then finally, you may merge this central into this, and you have all 6 points into one cluster. So this is bottom-up clustering, known as hierarchical agglomerative clustering, where in every iteration you merge one pair of clusters and keep on repeating this until you reach the one cluster which contains all data points. All clusters are merged into one. So now what is the clustering? So now and it shows the sequence of grouping of data points. And now if you want to generate 3 clusters out of this, you can do it. If you generate 2 clusters out of this, you can do it. And if you want to generate 4 clusters out of this, you can do it also. So to generate 2 clusters, you can cut from here. If you cut from here, you get 2 clusters. If you cut from here, you get 3 clusters. How many? 1, 2, 3, 4, 5 clusters. Right. So in this example, it seems like 3 clusters is a good solution. If you after running this hierarchical agglomerative clustering and generating dendrite, if you say that show me 3 clusters, it will show these 3 clusters, which are same as what we did with k-means clustering. No, slightly different from that. But maybe after the similarity, the way we calculated might be a bit different. Right? But this is hierarchical agglomerative clustering, and this is how it works. So on this Saturday, we'll do this clustering technique in laboratory, and we'll also answer that is answer if you have doubts on this. It's already 2:30, so I will not wait for doubts. But again, we can discuss this things on Saturday. Thank you.